Welcome to Systemic Stack. This is episode 4 of the System Engineering series, and today we will explore CAP Theorem practical application in a way that helps you to prepare for system engineering interviews on this topic. See, when a network split hits, you've got to make a choice, right? Your ability to justify that trade-off is exactly what an interviewer wants to hear. We'll go beyond basic definitions so you can confidently defend architectural decisions for real-world systems like Cassandra or MongoDB. We'll begin by breaking down the three pillars of the CAP theorem to see how they actually function in a distributed environment. You're going to see why consistency and availability often pull in opposite directions when a network partition happens, which is, the inevitable reality we face in production. We'll spend some time debunking the common pick two myth, because in actual system design, you don't just pick two and walk away. You make a deliberate choice about how your system behaves when things break. This is a critical area for interviews, so we look at how to justify choosing a CP or AP architecture based on real business needs, like comparing a high-stakes banking ledger to a high-volume social media feed. Finally, we'll see how databases like Cassandra and MongoDB handle these trade-offs through quorum tuning. And we'll even look beyond CAP to the Pasilex theorem to understand performance during normal operations. By the end, you'll have the framework to justify architectural decisions that balance data integrity with system uptime. The CAP triangle is basically the fundamental law of the distributed world, and it's the first thing an interviewer will look for when you're discussing scaling. It works by mapping out three competing goals: consistency, availability, and partition tolerance. Now here's the thing. While we want all three, the theorem proves that in the presence of a network partition, you have to trade one off. What matters here is that your choice defines how the system handles pressure. If you try to force all three, you'll end up with a system that deadlocks or produces conflicting data when the network gets flaky. The failure mode here is a total lack of predictability. Without a clear strategy on this triangle, you can't guarantee what a user will see after they hit save. In an interview, you need to show you understand that this isn't about picking your favorite two features. It's about deciding which failure you're willing to tolerate to keep the business running. Consistency in the CAP sense is all about ensuring that every node in your cluster sees the same data at the same time. When you perform a write, the system works by broadcasting that update and waiting for confirmation before it tells the user the job is done. What matters here is that it prevents what we call dirty reads, where one user sees a bank balance of $100 while another sees zero. If consistency isn't handled correctly, the failure mode is a fractured state, where different parts of your application are making decisions based on conflicting information. In an interview, when you're asked about consistency, it's a great chance to mention that this isn't just about being right. It's about the performance bottleneck that occurs because nodes have to talk to each other before finishing a task. If the network is slow, your consistency guarantees will make the entire system feel sluggish or even time out for the end user. Now, it's important to realize that consistency isn't just a binary on-off switch, it's actually a spectrum. On one end, you've got strong consistency or linearizability, where every single node is updated immediately. This is great for accuracy but can be a huge performance killer. On the other end, we have eventual consistency, which lets the system respond quickly while syncing nodes in the background. What matters here is that choosing the wrong spot on this spectrum can lead to massive latency issues. If you demand strong consistency across the globe, your system's failure mode is extreme slowness, as every request waits on a slow transoceanic cable. In an interview, you'll want to discuss this as a trade-off between user experience and data correctness. If you can tolerate a user seeing a slightly older comment for a few seconds, eventual consistency might be the way to go. But for things like inventory levels, you probably need to stay on the stronger side. Partition tolerance is often the most misunderstood part of CAP. It works by ensuring the system keeps running even if the network between nodes goes down or starts dropping messages. We call these network partitions. What matters here is that in the real world, networks aren't perfect. Cables get cut, routers fail, and packets just disappear. If your system doesn't have partition tolerance, the failure mode is a complete cluster collapse the moment a single network link gets shaky. In an interview, you should emphasize that P is essentially a cost of doing business in a distributed system. You can't just wish away network failures. If you're designing something that lives on more than one machine, you're effectively forced to deal with partitions. The real question isn't whether you want partition tolerance, but how your system behaves when the partition inevitably happens. Do you stop all traffic to stay consistent, or do you keep serving users and sort out the data mess later? So, why do we say P is non-negotiable? Well, if you're building a distributed system, you're inherently using a network, and networks are statistically guaranteed to fail at some point. This is why you can't actually choose a CA system for a distributed environment. What matters here is that if you try to ignore P, you're designing for a fantasy world. When a real-world partition hits a system that hasn't planned for it, the failure mode is often a split-brain scenario where two different parts of your system think they're the master and start writing conflicting data. Interviewers love to see if you recognize this reality. If you suggest a CA architecture for a multi-region app, it shows a lack of understanding of physical constraints. The choice isn't C, A, and P, it's how you handle C and A when P occurs. You're either deciding to favor consistency and shut down temporarily, or you're favoring availability and accepting that some data might be out of sync. One of the biggest misconceptions people have is the pick two trap. It sounds simple, but it's actually a bit misleading. In reality, when the network is behaving perfectly, you can have both consistency and availability. The trade-off only kicks in the moment the network breaks. What matters here is that it changes how you think about system health. Most of the time, your system will look like it's doing everything right, but the failure mode appears when that one critical network link drops. That's when your predefined CAP strategy takes over. If you haven't planned for this, the system might flip-flop between states or crash under the pressure of trying to resolve conflicts it wasn't built to handle. In an interview setting, make sure you clarify that CAP is a design for the worst-case scenario. It's about what happens during the partition, not what happens during normal operation. Demonstrating that you know the difference between steady state and partition state is a huge signal for seniority. When a network partition actually hits, you're forced into a fork in the road. You can either cancel the operation to maintain consistency, which we call a CP system, or you can proceed with the operation to maintain availability, which is an AP system. This works by setting a strict protocol for how nodes respond when they can't talk to their peers. What matters here is that it directly impacts your user's experience during a crisis. If you go the CP route, a user might see an error message saying service unavailable. If you go AP, they might see a version of their profile that's 5 minutes old. The failure mode of making the wrong choice here can be devastating. For example, if you choose AP for a money transfer, you could end up with double spending. If you choose CP for a social media feed, your site goes dark just because one data center is having trouble. You have to match the trade-off to the specific business risk. Let's talk about CP systems, which prioritize consistency and partition tolerance. These systems work by ensuring that if a node can't confirm a write with the rest of the cluster, it simply refuses to perform the operation. What matters here is that it guarantees that your data is always accurate and synchronized across all points. You'll see this in systems like Zookeeper or many traditional relational databases. However, the trade-off is clear. The failure mode here is downtime. If the network splits, the minority side of the cluster will stop accepting requests to prevent data divergence. In an interview, you justify a CP choice by explaining that data integrity is your absolute top priority and that providing stale data is worse than providing no data at all. Just keep in mind that the bottleneck here is the consensus mechanism. Every write needs a majority of nodes to agree. So if your network has high latency, your write performance is going to take a significant hit. On the other side of the coin, we have AP systems, which favor availability and partition tolerance. These systems work by allowing every node to keep responding to reads and writes, even if they can't talk to the rest of the cluster. What matters here for high-scale applications, where being offline is the ultimate failure. Think about a shopping cart or a social media feed. You want the user to keep interacting, even if the backend is struggling to sync up. But there's a catch. The failure mode here is inconsistency. You might end up with conflicting updates that have to be resolved later, often using complex logic like last write wins or vector clocks. When discussing this in an interview, you should mention that while the system stays online, the complexity shifts to the application layer to handle those data conflicts. The bottleneck isn't the consensus anymore. It's the eventual synchronization process that has to merge all those divergent states back into a single truth. We often hear about CA systems where you supposedly have both consistency and availability. In theory, this works perfectly as long as the network is flawless. But in any distributed environment, the network is never flawless. This is why a CA system is essentially a myth for anything spanning multiple nodes. If you claim a system is CA in an interview, you're basically assuming messages are never dropped or delayed, which is a massive red flag. Why does this matter? Because if you build a CA system and a partition actually happens, the system has no protocol to follow. It will either stop responding entirely or it will allow inconsistent data to propagate without any way to reconcile it. That failure mode can lead to corrupted databases that are nightmares to clean up. In the real world, you have to acknowledge that P is a fact of life, so your architecture must be either CP or AP. CA is really only a valid concept for a single node database where there's no network to split. Making the right design decision comes down to one question: what's the cost of being wrong versus the cost of being offline? This works by evaluating your specific use case against the CAP trade-offs. What matters here is that there's no such thing as a best database. There's only the best database for your problem. If you're building a medical record system, a failure to show the latest medication could be life-threatening, so you'd lean towards CP. But if you're building a gaming leaderboard, being offline for an hour is a much bigger disaster than someone seeing the second place score for an extra minute. In an interview, the key is to show you can map these technical trade-offs back to business requirements. The failure mode of ignoring the business context is over-engineering a system that's either too slow or too unreliable for what the users actually need. Always start with the requirements, then use CAP to justify your architectural path. Let's look at two contrasting examples. Banking versus social media. A banking system has to be CP. It works by ensuring that if a node can't verify a balance, it errors out. What matters here is that an incorrect balance isn't just a bug, it's a financial and legal disaster. The failure mode for a bank is a rejected transaction, which is annoying but much better than losing money. Now compare that to a social media feed, which is typically an AP system. It works by showing you whatever data is closest to you. Why? Because seeing a post from 10 minutes ago is a much better user experience than seeing a 503 service unavailable error. The failure mode here is just a slightly stale feed, which most users won't even notice. In a system design interview, using these kinds of clear high-stakes comparisons shows that you understand how CAP isn't just an abstract theory, but a practical tool for protecting the core value of an application. A classic real-world example of an AP-leaning system is Apache Cassandra. It's designed to be highly available and partition-tolerant from the ground up. It works by using a peer-to-peer architecture where any node can handle any request. What matters here is that it allows for massive horizontal scaling without a single point of failure. If a few nodes go down or the network splits, Cassandra just keeps on chugging. However, the trade-off is that it relies on eventual consistency. The failure mode is that two users might see different versions of the same row for a brief period. To mitigate this, Cassandra offers tunable consistency, which lets you decide on a per-query basis how many nodes need to agree. In an interview, mentioning Cassandra is a great way to show you know how modern databases implement CAP. It proves you understand that you can actually move the needle between A and C depending on what a specific part of your app needs at that moment. As you get more advanced, you will find that CAP doesn't tell the whole story. That's where the pass-select theorem comes in. It works by extending CAP to describe how a system behaves during normal operation, not just during a partition. The acronym stands for: if there is a partition P, choose between availability A and consistency C. Else E, choose between latency L and consistency C. What matters here is that it forces you to think about performance when everything is running fine. If you want strong consistency even when there's no partition, your system is going to be slower because of the extra communication overhead. The failure mode of a pass-select unaware design is a system that's unexpectedly slow during peak times because you over-optimized for a consistency level you didn't really need. In an interview, bringing up pass-select shows a deep, nuanced understanding of distributed systems. It shows you're thinking about the 99% of the time when the network is healthy, as well as the 1% when it's not. So let's pull this all together. We've seen that the CAP theorem isn't just an abstract triangle. It's a framework for making hard choices when the network inevitably fails. Since partition tolerance is non-negotiable in distributed systems, the real decision happens during a split. Do you prioritize consistency or availability? In an interview, a strong answer shows you understand that CP systems like MongoDB favor data integrity over uptime, while AP systems like Cassandra keep the lights on even if the data is slightly stale. It's about matching the system's behavior to the specific business requirements. Well, now you can move past the pick two myth and explain exactly how a system handles a crisis. You've got the mental model to justify whether a read should return the absolute latest data or just a fast response. And that's exactly the kind of trade-off reasoning that shows you're ready for high-level architecture discussions. That wraps up a look at CAP in the real world. Now, when you're in an interview, remember it is not only about memorizing the acronym. You've got to justify your choices, like why you'd pick MongoDB's consistency over availability during a partition split. Showing you can tune quorums or explain PASELC really signals that you understand the nuances of high-scale systems. If you found this helpful, hit subscribe. In the next episode, we will discuss consistency models, strong, eventual, causal, where we will discuss core understanding, strong consistency, eventual consistency. Catch you then and good luck.